Hi everyone, we are Team Hedgehogs and our project is an ultrasonic receiver. My name is Abhinav Daga.
My name is Takumi Hayashi. My name is Ang Li. Tianyu Yang also in our team.
So here we have our measurement setup, which we will use to demonstrate the functionality of our chip. On the right hand side here, we have the transmitter, which is fed a square wave modulated 40 kHz signal. The transmitted output has some channel delay depending on the speed of sound multiplied by the range between the transmitter and receiver, and after the channel delay the signal is received by the receiver transducer directly fed to the input of our receiver, and the receiver gives a digitized output. So here we can see on the blue channel 3 that is the transmitted signal. On the green channel 2 we can see the signal received by our device, and on the yellow channel 1 we can see the digitized output of our receiver when it detects a 40 kHz signal. Okay, so now let's carry out some distance measurement. In our present setup we have measured a delay of approximately 540 microseconds. Let's feed that into our calculator, and we already have that, and that corresponds to a distance of approximately 16.6 centimeters. So the distance measured using our ruler is also 16.5-ish centimeters. So our accuracy is pretty close. Now let's carry out a measurement with some moderate distance. So as you can see, the time delay has increased. Let's place the cursor on top of the received signal. So here the delay is approximately 2.08 milliseconds. Let's feed that into our calculator, and we can see that we measured a distance of approximately 69 centimeters. And as you can see, the distance that we actually measured is slightly higher than 68 centimeters. So again, this is fairly close to what we expect. Let's carry out a higher distance measurement to wrap up our demonstration session. Okay, so here we have approximately 3.4 milliseconds of delay. Let's feed that in our calculator, and we see that the distance is around 114 centimeters. And the actual distance is approximately 112.5 centimeters. Again, we are fairly close. Some sources of error in our setup can be multipath interference and also the least count of the oscilloscope, which is around 20 microseconds, corresponding to 0.7 centimeters.
So our signal received by our system will first with input of our LNAs and output of our comparator digital output. Our system are including the amplification, filterings, envelope, and finally single-digit analog to digital conversion stage will give us output of the digital signal. For our amplification stage are including the LNA and 2 stage of PGAs. The LNA has the amplification of 14 decibels, and 2 PGA combines give us maximum of 40 dB amplifications in total. So our amplification stage will give us 54 decibels of amplifications, which allowed us to detect the object at a longer distance with very low amplitude of ultrasonic received. The first low-pass filters with cutoff frequency and 110 kHz, which will keep our desired ultrasonic signal at 40 kHz, at the same time filter out unwanted high-frequency noise. The cleaned signal will be sent to our envelope detectors. Our envelope detectors are able to create a low frequency envelope, but at the same time will create a spurious 80 kHz signals, which we are required for our second low pass filters to filter out this high frequency spurious signals. Our second low pass filters have a frequency of 10 kHz that will keep our low frequency envelope, which is typically from 10 to 100 Hz, to have a clean envelope signals that we are able to send for the comparators. After the envelope stage, we have another OTAs with output feedback, with our resistive output feedback, have more capability to adjust the signal amplifications. Then the process signal will be sent to our comparators, which will translate our analog signal to the digital one, which have a clear reference between the initial and delay signal. That's allowed us to have a constant reference during the distance measurement with our ultrasonic sensor.
So this is our PCB circuit design. On our design, on the top left, we have an ultrasonic receiver. The signal received here, the fed of the ultrasonic receiver chip in the socket. The output of the signal will be the probe on the pin of the socket. On the top right, we have a potentiometers to adjust the bias voltage reference to the device. In the middle, we have jumpers to control the gain of the PGAs. On the bottom left, we have a potentiometers to make up the resistive feedback to the OTA at the mixer output. On the right and around the PCB, we have some decoupling capacitors for stable operation circuits.